In the case of normal stress and the normal strain, the strain energy is given as the area under the stress strain diagram, and up to elastic limit we have an expression for strain energy is given as strain energy density U is given as integral from 0 to epsilon of sigma x multiplied by d epsilon x. So if you integrate this, you will get this area. Here sigma x means the height of this rectangle, and the width of this rectangle is denoted as d epsilon x, and the height is same as sigma x. And we can use the equation for the proportional limit, that is up to yield point. We have Young modulus E is same as sigma x divided by epsilon x, that is we have normal stress upon normal strain. Now almost same idea we can use in the case of shearing stresses, and we can develop the expression for elastic strain energy in the case of shearing stress. So if the state of a stress is represented by purely the shear, that equal to tau xy, and this is also equal to tau xy, in that case the angle subtended between the two perpendicular edges is called as shear strain and is given as pi by 2 minus gamma xy. And there exists a relation between the shear stress and the shear strain, that is called as the modulus of G is given as tau xy divided by the shear strain gamma xy. Now similar to the stress versus strain diagram, if we use the shear stress versus the shear strain diagram, then this area will represent here the elastic strain energy for shearing stress. So almost same concept we'll use here. We'll consider here one rectangle. Now this rectangle has a constant width of d gamma xy. So width of this one is same as d gamma xy, same as d epsilon x, and the height of this rectangle is tau xy. So we can also calculate here the strain energy density almost using the same formula. So we have strain energy density U is equal to integral from 0 to epsilon, that is the normal strain. So this time it's a gamma xy, and the height of this rectangle is tau xy. So we have tau xy, and the width is equal to d gamma xy. In this case, the gamma xy is the shearing strain corresponding to the shear stress equal to tau xy. Energy density is nothing but the area of OAB, and this area is same as equal to 1 by 2. We have height is equal to tau xy, and the width is equal to gamma xy. In this case, we can replace here gamma xy as tau xy divided by g. So we have 1 by 2 into tau xy. Gamma xy will replace as tau xy divided by modulus of ut equal to g. So almost same expression you will get in the case of shear stress also, that equal to 1 by 2 multiplied by tau xy square of it divided by g. So this one is the strain energy U, which is nothing but the du divided by dv. In this case, the last expression we have U is equal to integral 0 to epsilon x sigma x d epsilon x. So again, if I consider here the triangle, that is the area under the triangle AOAB. So we will get here the strain energy U will be equal to 1 by 2 multiplied by sigma x multiplied by epsilon x, and we can replace here epsilon x again by sigma x by Young modulus E. So we'll get this value equal to 1 by 2 into sigma x multiplied by sigma x divided by Young modulus E. So almost similar situation arises in the case of the normal stress and the shear stress. So finally we are getting here 1 by 2 into sigma x square divided by Young modulus E, and this strain energy density is same as du divided by dv. dv represents here the change in volume. So we have du, that is the strain energy stored in the element, will be equal to 1 by 2 multiplied by tau xy. We have square of it divided by modulus of g equal to g multiplied by dV. So if you integrate the above equation, in that case we can calculate the elastic strain energy associated with the shear deformation of the body, and we have total shear strain energy U will be equal to integral of 1 by 2 into tau xy square of it divided by the modulus of dt equal to g dV. This expression is almost same expression that we obtained in the case of uniaxial normal stress. That is, we have total strain energy U is same as equal to integral 1 by 2 multiplied by sigma x square divided by young modulus E multiplied by dV. So both these equations are identical equations. One is used for normal stress, other is used for shear stress. And here the young modulus E and the modulus of GDG are related by the term young modulus is equal to 2 times of modulus of GD multiplied by 1 plus mu, where mu is a Poisson ratio. So we can very well replace the value of G in denominator. So we have modulus of GD is equal to E divided by 2 times 1 plus Poisson ratio mu. So we have total strain energy will be equal to U integral of 1 by 2 tau x square as it is. So we have tau xy square divided by G. G is replaced as E. This denominator will shift in numerator will be multiplied by 2 into 1 plus mu multiplied by dV. So 2 is get cancelled, and final expression you will get as integral of tau xy square divided by E into 1 plus mu multiplied by dV. So this alternate expression can also be used, or otherwise you can calculate the value of G from known value of young modulus, which is equal to E upon 2 times of 1 plus Poisson ratio. So you remember this equation to calculate the strain energy in the case of normal stress, and you remember this equation to calculate the strain energy in the case of shear stress. Once we know the elastic strain energy associated with the shear stress, with the shear deformation of a body, that is, we have U is equal to 1 by 2 into shear stress square divided by modulus of it equal to G multiplied by dV. We can calculate here what is the strain energy in the case of torsion. So we'll consider here one shaft which is subjected to twisting couple equal to T, and the length of the shaft is equal to L. The diameter of the shaft is equal to D, and we know the torsion formula, that is, we have torque divided by polar moment of inertia J is equal to the shear stress at any radius, that will represent as tau xy divided by the radius r, and is also equal to the maximum value of the shear stress divided by the outer surface radius equal to r in the case of solid shaft. Now we want to replace here tau xy, so we have tau xy will be same as equal to torque multiplied by r divided by J, that is the polar moment of inertia. So this one is a situation in which we have a constant cross section. We'll want to make here a generalized equation. To make a generalized equation here, we'll consider here a shaft BC of length equal to L and is subjected to torque equal to T, and we'll consider here one element at a distance equal to x from the fixed end, and let's say the area of this element will be equal to dA, and let's say we have thickness or the length of this element equal to dx. So this length we'll consider equal to dx. So the area is equal to dA, length equal to dx, so we can replace here dV, and we can write the value of dV is equal to dA multiplied by dx. So in this case we'll replace the shear stress equal to torque multiplied by r divided by J, and dV will replace as dA multiplied by dx in the above equation. So we have total strain energy in the case of torsion is given by integral 1 by 2. We can replace here tau xy is equal to T square into R square divided by G, and we have tau xy, so one value of J is left and we have to make a square of it, and the value of dV we can write as a product of dA multiplied by dx. This term of r square dA will combine into one bracket. So we'll get the integral 1 by 2 into T square divided by G divided by J square, and we'll write this integral again R square dA. Now this one is nothing but the polar moment of inertia multiplied by dx, and since we have integration is with respect to dx, so we have lower limit of x is 0 and the upper limit is equal to L, and this value will replace as the polar moment of inertia, that is this value is replaced by J. So we have integral 0 to L T square divided by 2 times of G into J square. This term will replace as J multiplied by dx. So total strain energy is given as integral 0 to L T square. One of the J will be cancelled, so we have T square divided by 2 times of Gj multiplied by dx. So you can use this equation when we have a variable cross section and the torque is also variable. But if the torque is remain constant, in this case for this figure we can take out here T square by 2 Gj common. So suppose we have a uniform cross section and is subjected to the torque T at its end, then the value of T square divided by 2 times of Gj can be taken outside. Integral of dx is same as equal to x, upper limit is equal to L, lower limit is 0, that will be equal to L. So when we have a shaft of uniform cross section, then the strain energy is given as T square multiplied by L divided by 2 times of Gj, where J is called as the polar moment of inertia. So we can calculate here the strain energy due to torsion using the integral 0 to L T square divided by 2 times Gj multiplied by dx if we have number of torque and the section is variable section. And for a uniform section we can use the strain energy equal to T square L divided by 2 times of Gj. So we'll continue our derivation in the case of uniform cross section. We have strain energy is given as T square L by 2 times of G by J. Since we have a solid shaft here, the torque is given by torsion formula will be equal to pi divided by 16 multiplied by shear stress tau multiplied by dq. So we can put this value back here and we'll try to solve this, and J will be given as pi by 32 d to the power 4. So we have strain energy U in the case of torsion will be equal to T square. T square is same as pi square divided by 16 square multiplied by tau square multiplied by d cube square, that will be d to the power 6 divided by 2 times of G multiplied by length L, and is divided by polar moment of inertia which is pi, and 32 will shift in numerator. So we have pi by 32 d to the power 4. So in this case one of the pi will be get cancelled. This is d to the power 6 and d to the power 4. So d to the power 4 is get cancelled, and instead of 6 we have power is 2, that is we have d square, and we have 32 and 16 square divided by 2, that is the denominator will be left same as equal to 16. 16 into 16 into 2 is 32. 32 get cancelled, and we have strain energy U is equal to pi into d square into L divided by 16 multiplied by tau square divided by G. Now as far as the volume of the given shaft is considered is pi by 4 multiplied by d square multiplied by L. So we'll adjust this 4 here and we can write this term equal to volume V. So we have U is equal to tau square divided by 4 times of G. So 1 4 you have to adjust as pi by 4 multiplied by d square multiplied by L. This is nothing but volume. So we have total strain energy U equal to tau square divided by 4 times of modulus of rigidity G multiplied by volume V. So the strain energy density U in the case of torsion is U divided by V is equal to tau square divided by 4 times of G. So in the case of torsion, the strain energy density is given as tau square divided by 4 times of G. And in the case of the shear stress, we have strain energy density U is equal to 1 by 2 tau square xy divided by g. And in the case of the strain energy density due to the shear stress or the shear force, the strain energy density due to the shear stress or shear force is given as tau xy square divided by 2 times of g, and in the torsion it will be tau square divided by 4g. So there is a difference in the strain energy density due to the shear force and due to the torsion. A block of 200 by 50 mm by 70 mm is subjected to shear force of 20 kN. Take the modulus of GD equal to 8 into 10 to the power 4 Newton per mm square is megapascal. The strain energy stored in the body due to shear stress we have to find out in Newton mm. So here the top plane is of dimension equal to 200 mm by 50 mm, and to this plane the force of 20 kN is acting parallel. So this force divided by the area, we can calculate here shear stress, let's say tau xy, and we are interested in the strain energy. Strain energy per unit volume is given as 1 by 2 tau xy square divided by g, and since we are able to calculate the volume of the given element, we are able to calculate here total strain energy in Newton mm. So first we calculate here what is the shear stress developed tau xy. Here force is equal to 20,000, that will be Newton, and we have area of the top plane will be equal to 200 multiplied by 50. This answer will come in megapascal. So we'll get this shear stress will be equal to 2 megapascal. So total strain energy U will be equal to strain energy density multiplied by volume. So we have strain energy density is equal to 1 by 2. We have tau xy square divided by g. This is megapascal and this one is megapascal, so 1 megapascal is left. 1 megapascal is same as Newton per mm square is megapascal, and we have volume is A, which one is 200, B is equal to 70, and C is equal to 50. So if I take a product of A into B into C, that will be mm cube. Our answer will come in Newton mm. So total strain is equal to 1 by 2. Shear stress equal to 2, that you take in megapascal, so we have 2 square. G you have to take in megapascal, that is same as Newton per mm square is 8 into 10 to the power 4. And ABC, all these dimension you take in mm. So we have 200 multiplied by 70 multiplied by 50. So total strain energy U will be equal to 17.5 Newton, and one of the mm will left in the numerator, so it is Newton mm. 17.5 Newton mm. The video you are watching is from the app, which is the Mohod class app available on Google Store, and in this app we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.